You're listening to a podcast from 702 and Cape Talk.
There, yes.
702 and Cape Talk.
The Naked Scientist.
I'm sorry, that was not me pressing the wrong button. It's just me talking too much. Dr. Chris, are you there now?
Hello, good morning.
Good morning. You are down under, I believe.
Well, so are you. So I suppose we can say we're actually in the same hemisphere. But yes, I'm in Perth in Western Australia.
You see, you can never make a joke to a scientist, can you? You can never, without being corrected. I have scientific parents, same problem, trying to be clever, and that's what happens. Yes, okay, you are at a conference in Perth, and there are lots of other clever people around you.
Oh, yeah, it's been amazing. I think probably it's the best conference I've ever been to. It's a biomedical science conference, so they've got people who are doing things relevant to health and medicine. And it's called Science on the Swan. And I was actually speaking at the conference, but I was speaking more about how you make science fun and interesting to people rather than making big scientific discoveries. But I did go to all of the talks, and I've learned so much. I mean, the most impressive one, there was this chap who turned up from Melbourne on the east coast of Australia. And he was showing pictures of how he's got a system for when you go inside an artery to unblock an artery. If you have, say, heart disease, and it's caused by the narrowing of an artery that supplies the heart, one way to treat it is to put some dye into the artery and look with X-rays to see where the artery is narrowed, and then you can blow up a balloon inside the narrowed area to open the artery back up, and then you put a wire cage called a stent in there. But obviously what you're looking at is a two-dimensional image from outside the body just viewed through the body. So there's a limit to how good the images can be. So what this chap is doing, and this is becoming quite widespread, this technique, it's called optical coherence tomography, which is a posh way of saying that you actually have a tiny camera, which is about as big as the end of a human hair, inside an artery. You thread this in from outside the body through, say, the arm or the leg, get into the artery of the heart, and it uses infrared light to illuminate the wall of the artery, and then it picks up, using a tiny camera, the light bouncing off the inside of the artery, and it projects it to the operator so they can actually see what the inside of the artery looks like. And you can see where the damage is in the wall, you can see whether the wall is furred up, or if there's a problem waiting to happen, you can see what the stent looks like when you put it in. It's just amazing.
That is extraordinary, I have to say. And of course, I presume it's more accurate. It will also then prevent any problems, because sometimes they do experience problems with these kind of procedures, where they don't quite recognize just how thin the walls are, etc.
Well, the thing is that up until now, we've been able to look from outside the body, see where the narrowings are in arteries, and then open them up to restore blood flow or improve blood flow to the heart. And this usually results in fewer symptoms for the patient. But often, if a person has an area of the artery that's not very narrowed, it can nonetheless be what we call unstable. It could be a region of the artery that is about to break, which could lead to the formation of a blood clot, which could block the artery and cause a heart attack. And you can't tell that necessarily from looking outside the body. But with this new technique of looking from the inside of the artery, you can see where these hot spots are, effectively heart attacks waiting to happen. And you can go in and intervene in those areas preferentially, and therefore prevent the problem of the person having problems downstream.
Just extraordinary things. We actually have a question here that came in by email where somebody is asking, can 3D printing, it's not quite the same thing but related, can 3D printing successfully make individual replacement teeth? And would that be cheaper than the current methods?
Well, one of the other sessions at this conference in the last couple of days was looking at whole new body parts. There was one gentleman who actually is from South Africa originally. He's now a surgeon doing spinal surgery in Perth. And one of the things he was presenting were ways of making models of the spine. You get very accurate scan data. You then make a 3D printed model of the anatomy so that then you can work with designers and various other engineering companies to produce prostheses like new discs, for example, that can be placed into the damaged area of the spine to stabilize it. Or you can actually 3D print using cells and things like that. It was one of the other talks, to make new body parts which are much more akin to what would be in your body already, using even your own cells to do it, so that you can produce replacement organs. Now, we're a bit of a way away at the moment from producing whole new organs that can be plumbed in. But certainly in the future, we're going to be in the stage where we can 3D print things like teeth, things like bones, things like even lung, maybe even kidney.
That's absolutely extraordinary. We have our first caller, who is Roger from Newlands. Roger, you're welcome.
Hi. Yeah, the question is, in your car, when your window's mist up, you can add air or you can add heat to get the mist away. But why does it, when you go away so quickly when you switch your air conditioning on? Something less technical.
Oh, yes, an excellent question. And the reason for this is that the aircon air is much drier than the non-aircon air. Why is it much drier? The way an air conditioner works is it uses some of the energy from the engine. You have a compressor under the bonnet, which is driven by the engine, and this runs effectively a fridge inside the engine compartment, and the air passes over a very cold element, because in the same way as your fridge has a freezer compartment, and it makes the air inside the fridge cold, as the air is drawn in through the air conditioner, it passes over this freezing cold element, and in the same way that you get frost in your freezer because it pulls the water out of the air, leaving cold, dry air, the air that's coming into your car is therefore made extremely cold because the water condenses out of it, because cold air can't carry very much water. If you blow very dry air onto your windscreen, the water that's on the windscreen already, because the windscreen's a bit warmer than the air-conditioned air, the air-conditioned air is dry and will pick up heat and the water from the windscreen, removing the condensation.
Roger, thank you for that, because I tell you, I've often wondered that myself. My Mini constantly does that, and it only works if I put on the aircon. So thank you for that question. Dennis and Benoni?
Hello, Chris. I want to ask a question about helicopter. When a helicopter is on the ground, the blades, they bend over very flimsily down, and it looks like it's absolutely impossible that it can actually carry the load. But yet when it starts up, they straighten, but they don't break. Is there something special about a helicopter blade why it does not break when it lifts up to the ground? Because when it's resting, they look extremely flimsy. Is there an explanation for that?
Yeah, they're not flimsy. If you think about how fast it's going, and you think about where the lift is coming from that's lifting the helicopter, in order for the helicopter to hover in the air, it must be generating as much lift as the force of gravity is trying to pull it down. Therefore, the weight of the helicopter must be being suspended by its mass divided by the number of blades. So if there's, say, 4 blades, one blade must be able to carry a quarter of the mass of the helicopter, because that blade is generating the lift, which equals the force that the helicopter is trying to fall down towards the ground with. Are you with me?
Are you with him? No, I think he might be gone. He's listening. Keep going. Chris.
But anyway, so the bottom line is that the helicopter blades are incredibly strong, and it's the same as your aeroplane wings. When you look out of the side or the window of an aircraft and the wings appear to be going up and down a bit, the fact is those wings are lifting up the entire aircraft. And if you have a big aircraft which weighs, say, 200 tons, big passenger aircraft with all the fuel and all the passengers on board, maybe even 250 tons at takeoff, then that lift has to come from the wings, and therefore the wings are lifting up the aeroplane. And therefore the wings have to be able to support the aircraft. They may look flimsy, but they're incredibly strong, and they have some give in them, because they have to have, in order to meet the demands of the environment. They've got to be able to heat up and cool down as the aircraft travels through the air and stops and gets heated up by the sun, so there's got to be a bit of expansion and contraction. But the actual mechanical engineering of these materials is incredible, and they're incredibly tough. And when those blades spin out, they're stretched outwards, because on a helicopter, back on helicopters now, when the blades are spinning, they're pulled out, and there's a centrifugal acceleration and outwards force, which means that they actually stiffen, and they're also controlled from inside the helicopter to change the pitch of the blade as well, which adjusts how much lift they generate and how the helicopter actually turns and steers. And all those things will change the attitude of the blade, but they are really strong, believe you me.
Well, that's good to hear. I think everybody would be relieved to hear that. Please continue sending us in your questions, 011 883 0702 or 021 446 0567, or else 31702 or 31567.
702 and Cape Talk.
The Naked Scientist.
Welcome back. We're talking to Dr. Chris Smith, as always, who is down in Australia. Please keep on sending in your questions. It's now gone 18 minutes past 10, so you just have about less than 10 minutes to send in your questions. 011 883 0702 or 021 446 0567. Lisa and Steve will be to you shortly. Alfred?
Good morning, Zabata.
Good morning. Thank you for holding on. What's your question?
Yes, I'd like to ask the scientist, when someone snores, okay, the terrible rackets made by them, they don't wake them up, but they always say, they're light sleepers, the slightest noise will actually sort of wake them up. Why is that? I know it's like a subconscious thing. It's just strange, I just want to know, from the scientists.
Why doesn't their own snoring wake them up? Is that what you're asking?
Yeah, hi, Alfred. I don't know the answer to this, but I'm going to speculate based on what I do know, which is that there is a special region of the brain, and it is at the temporoparietal occipital junction, which is a posh way of saying it's in the region of the brain where the temporal lobe, roughly adjacent where your ear is, and the bit of your brain at the back, above your ear, and the bit of your brain at the very back, sort of if you carried on from your ear, where those three areas meet, scientists have identified a special region which appears to have a role in cancelling out what the brain expects to come in the way of stimuli. So, for instance, if you tickle yourself or you tickle your skin, you don't actually respond in the same way that a person who didn't expect you to tickle them responds when you tickle them. Because the brain, it's almost as though it knows that you're executing that particular movement or you're making that particular movement, and so it expects to have that particular set of stimuli, the tickle stimuli, coming in, and so it subtracts one from the other. And the idea of this is that you don't get distracted by internally generated stimuli, so that you can pay attention to things coming in from outside and around you. And the thing is, let's face it, if you think about evolutionary past, if you were sitting out there on the veldt somewhere and there was something creeping up on you who might attack you and turn you into its lunch, if you're too busy being distracted by signals coming from your own body, you might not notice that thing trying to eat you or creep up on you to catch you. And so we think that's why your brain does this. And if you extrapolate that to when you're asleep and snoring, because you know you're taking a breath and the brain is therefore primed to make some noise and sound as you breathe in, it's likely that you will subtract away from your attention what's presented to the attention centres in the brain, those anticipated stimuli, so you don't wake up. Now, that's my theory. I don't know it's absolutely true, but that's what I'm speculating. But if anyone knows better, of course, do tell us.
I can now hear about 20,000 women or 200,000 or 2 million women saying, could they not figure out, those clever people, a way to stimulate that part of my brain so that I don't have to hear my husband or partner snoring. Lisa in Sea Point. Hello.
Hi, good morning. Thank you very much for taking my call. The question is, how far are we in reaching a cure or treatment for chemical?
Lisa, I'm sorry, your line is so bad. I'm going to ask the guys to call you back and see if they can get that better. Let's go to Richard in Midrand first. Richard, good morning.
Hello, Chris.
Go ahead, Richard.
Hello, Richard.
Hello. Hi, Chris. This is a bit of a humorous question, but I think it's a good question. When we are small, one of our biggest challenges is learning to tie different kinds of knots, beginning with our shoelaces. And it's quite a long learning curve, and then through Boy Scouts and so on. All the kind of knots one needs for securing things and so on. However, as you get older, a strange thing happens. With any piece of string, rope, computer cable, earphone cable, cell phone charger cable, hosepipe, whatever you could think of that has a reasonable length, just learns to tie its own knots all by itself. The most weirdest knots that have not even been developed by the best sailors, scouts, and so on. It's just weird. If you turn your back on anything, it will make its own knots. And intrigued about why this would happen.
Chris?
Yeah, hi, Richard. This is such a problem for everybody, and it's a problem for your own body, because just like your hosepipe ties itself in knots and your headphone cables tie themselves in knots, your DNA would also tie itself in knots if it wasn't carefully organised inside your cells. You've got about 100 trillion cells in your body, and each one of those human cells contains something like 2 meters of DNA, but it's coiled up inside a structure which is literally fractions of a millimetre across. I mean, your average cell is maybe 10 micrometers, so that's 1/100th of a millimetre across. It's got 2 meters of DNA coiled up in there. The way the human body solves this problem is it has little spools called nucleosomes made of protein, and the DNA gets wound up in a very organised way around those things. But extrapolating to your hosepipe, when you wind your hosepipe up, if you don't wind it carefully onto a spool which you can unwind it from again, then what you've got are a lot of loops of hosepipe or a lot of loops of headphone cable, and that's a very organised structure. If you pick that up, then there's a large number of ways that it can then go into disorder, and especially things that are coiled up in loops. If you've got loops of things, then loops can fall through the middle, and that's the first process in making a knot. And then along comes a toddler, or an older toddler, an adult toddler, and tries to undo this by becoming frustrated with it and giving it what we call in the business a bloody good shake. And what that does is introduce even more disorder and make more of the loops fall through more of the loops, and you get a tangle. And most people then become even more frustrated and give it a really good pull. And this tightens all of the loops that have been made inside loops, and as a result, you then end up with something you can't undo. It's because the way we want nature to be is very organised, and there are very few ways for things to be very organised, but there are lots of ways for things to be disorganised. And because the universe is moving from a state of order to disorder, it's inevitable that in the wrong hands, your hosepipe, your headphone cable, your electrical power cable will become tangled unless you take steps to wind it carefully onto a spool or unwind it extremely carefully to avoid it going into knots.
Chris, can I venture a guess that nothing in your house is untangled, is it? Or is tied into knots? Are you one of those very neat...
No, because the thing is that I had this sign. I had a teacher at school who had a sign on his desk that said, an untidy desk is a sign of genius.
Yeah, I
so
have that sign.
I decided that therefore it must be causal. And so if I have an untidy desk, I will become a genius.
Yeah, I have that sign.
I strive to become a genius.
Let's go to Andrew in 3 Anchor Bay. Andrew?
Hello, Doctor. I was always wondering how anti-inflammatories work, the sort of pharmacology involved. And I'm a very naive person in terms of the sciences of chemistry, of the chemist. I just want to find out how, how you take the tablets and it's really effective, particularly for migraine headaches and things like that. So I was just wondering...
Yep.
I'm very curious can I listen on air?
Yes, you're welcome.
Yeah, well, let's take a really simple example here. Let's take the example of aspirin, because aspirin's one of the oldest painkillers and the best known. It's more than 100 years old. Felix Hoffmann, working for the Bayer Pharmaceutical Company, invented aspirin. The posh name for aspirin is acetyl salicylate. And what aspirin does is it inhibits an enzyme called cyclooxygenase. And cyclooxygenase takes a chemical in your cells, which is called arachidonic acid, and it breaks it up into a different molecule, which is called prostaglandin. And prostaglandin excites pain nerves. It also excites blood vessels and makes them open up and makes things swell. So, if you take aspirin circulates in the body, and wherever it bumps into some cyclooxygenase enzyme, it irreversibly binds onto it and blocks it, so it can't work anymore. And that stops the enzyme turning arachidonic acid into prostaglandins. Now, there are some places in your body where you naturally make small amounts of these prostaglandins. One of them is in your kidney to control your blood pressure. The other is in the lining of your stomach to stop the stomach eating itself from your own stomach acid. But anywhere else in the body where you make prostaglandins, and essentially this cyclooxygenase enzyme, you're making it because there is inflammation going on. So when you pop a pill like aspirin or ibuprofen, which works the same way, paracetamol, Panadol works the same way, it cruises around the bloodstream, visiting all your cells, and if it sees or bumps into one of these cyclooxygenase molecules, it blocks it up and it stops the cyclooxygenase molecule making the inflammatory prostaglandins and other chemicals which are a bit similar, and as a result, the inflammation that would have occurred in that part of the body is damped down. And so that's how the painkiller effectively finds where it hurts. It doesn't, it goes everywhere, but you only make those chemicals that the painkiller switches off in the parts of the body that are damaged.
Oh, that's very interesting. Michael in Vereniging.
Hi, I've got a question regarding power sources for electric vehicles. You know, electric vehicles are limited to the distances they can travel, and also the weight they carry in terms of battery packs, that type of thing. And I was thinking about a solution to this problem, and I was thinking about a liquid-based power source. If you could positively charge a liquid or solution and, you know, use it in instead of fuel, like a normal petrol, you'd use a positively charged solution. Does something like that actually make sense? Can it be done?
Well, you're right to question the current situation with electric cars, because they are great and they're getting better all the time. But if you live in a country, especially like South Africa, where you can travel huge distances, Australia is another really good example, they're totally impractical if you need to go long distances. If you need to go short distances around the town, they're fantastic. But the current generation of electric cars, they weigh about 2 tons, of which 1.5 tons is the battery. Now, the designers have become quite ingenious, and they've turned things like the entire floor of the car into the battery compartment. So you have 1.5 tons of batteries sitting under your feet. They have also become very economical with where else they put the batteries and so on. They're still nonetheless not very energy dense. So the range that you'll get out of one of these cars is maybe 150 to 200 kilometres, and some of the newer generations might go a bit further, but the average is about that, which is not really enough, and people worry that they're going to run out of charge on the road somewhere, and it's currently holding the market back. So what researchers are doing is, and in fact there's a number of projects in a number of countries. Cambridge University is one place where this is being done. Researchers are trying to build better batteries, and one of the ways they're doing this is to just try different chemicals in batteries and try different combinations of chemicals to see if they can come up with batteries that can take a very high charging rate, they can deliver a lot of energy very quickly without burning out, and they can effectively hold a lot of energy in the first place. One way to do this might be to use batteries that work like a fuel cell, where you have a chemical reaction going on where they might use oxygen and you feed them hydrogen, for example, but then you've got the problems of carting around hydrogen. That's not ideal either. Another kind of battery is called an air battery. And in this kind of battery, you actually use air to circulate within the battery, and you have a chemical reaction going on with a chemical inside the battery and the air. And this produces a lot of energy. These sorts of batteries will fulfill some of the requirements, the fast charging, high current production, but we're still not there yet with a battery that's capable of storing enough energy in a compact enough form to make this really practical for the needs of all geographies. But for most people, if you're sitting in the traffic in Joburg, like I was doing quite recently, or Cape Town, then if you're doing just short distances, electric cars are absolutely brilliant. They don't produce pollution at source, they don't use any energy until you're moving, and they're most efficient when they're pulling away, unlike